Okay, welcome to the review section for the exam two. Today is the Friday, Monday is your exam two. I want to share the canvas with you first, just to make sure that you know where to find those information to prepare for the exam. So let me share the screen. Okay, and I'm going to share the canvas with you. So this is our webpage. Exam two is the 10th week. Believe or not, we already have through the semester. Today we're doing the review. There's a study guide, so you can click on the study guide to find the practice exam and also the video for the solution. Since there are videos for the solution, I won't repeat those things. That you can watch those video to figure out how to solve the problem in the practice exam. So it's a PDF, you can open it up. Today I'm going to post the solution as well, which you can see on paper if you don't want to spend time to watch the video. The video explain, how we get those solutions. So if you watch that, if you see that paper one, you still don't get it, then you can watch the video. There's some example that I put in this page, so you can see the second statement on this content. There's examples, and I update some of the example here. So if you wanted to look some more example, then you can click it here to see some example how to solve problem related to the topic. So that is this one that you can look. Let me go back. Let me get back. Okay. And also, let's see. There's a formula sheet that I put it here already that you can download it. So you can, like the exam that I gave you last time, you can write some notes, but you cannot include the workout problem. You can write, what's this symbol means, and etc. etc. So some of the things that you learned previously will be possibly be used here, which is the kinematics. So you can see the first table, which has like a two set of equations. One is for the rotational, the other one is for the linear motion. Linear motion is the topic that you learn from chapter 1 to chapter 5. So rotation is very similar to the linear motion. It just changed certain things. So here is the formula sheet that you can download before the exam. And one more thing is that exam only cover chapter 6 to 9. So we are going to skip chapter 10, even though chapter 10 is kind of practical for medical application as well. But we kind of slow on this semester, so I'm going to skip that chapter. And that is something that you should watch. Now, for honor section, you should watch the video in the honor section. There's two topics I want you to watch, which is chapter 6 and chapter 7, the work for non-constant force, impulse force integration. So these two topics, you should watch the video. That will be something in your exam, so you should watch that, know how to solve that. If I have time, I will give you one example for that for the honor section. All right, so that is the thing that you should know for the exam. Let me take a look something. One more thing is that I was grading your work, but then I noticed that some of you got even like more than 100% on the lab, and a lot of you actually got more than 100% on the lab. I don't know what happened, so I'm fixing it. So you are going to expect your grade will be lower because I don't know how they calculate that. They give you the lab, which is more than 100%. That's not possible. So you are going to expect your grade will be a little bit lower than what you see right now. All right, so the exam 2 on Monday start at 2 and 3 hours exam. So make sure they come in on time. We're going to have the exam in the lab, and chapter 6 to chapter 9. That is the plan. After the exam, we're going to talk about chapter 11. So that is what happened for the next week. All right, let me share the screen about the things I'm going to talk about for the review of today. Exam 2. Okay. All right. So I list some topics that I think is important for the exam 2 over here. So when you watch this video, then you will know what's not the most important thing that you should learn in this exam. The chapter 6, we start to talk about work and energy. And you need to know how to define work. And there's an equation to find a work, which is related to the force and also the distance. But the distance should be the distance along the direction of the force, or the force should be along the direction of the moving distance. So the working energy, you need to know how to get the work. And to determine the work, when we calculate the work, use the equation, which is this equation, force times the distance. When we calculate this, we assume this force is a constant. If force is a constant, then you can use this equation to find the work. For the honor section, you need to know what happens if force is not a constant. Force is not just a single number, it changes with the distance. Then how do you do the work? Then you actually require an integration. Then we started to find 2 different kinds of energy. One energy is called kinetic energy. Kinetic energy is related to the things is moving, which is related to the velocity. So kinetic energy is 1/2 mv squared. Potential energy has 2 different kinds. You have a U sub G, U sub S. They depends on the position. U sub G is the mgh, and U sub S is equal to 1/2 kx squared. Now this is not like obvious. It's different from the U sub G. So don't use like a mgx. It's not that. As a spring has to use the 1/2 kx squared. K is the spring constant. It also has a unit. The general form for the working energy, meaning if you wanted to change the energy, then you have to do work. So if you have kinetic energy at the beginning, you have a potential energy at the beginning, and you have maybe both, maybe with the spring as well. Then if you do some work, then you're going to have a different kinetic energy at the end, which is the final, and the U sub G at the final, and U sub S at the final. This is general form, meaning it is possible that you can have all these things happen in the system, but most of the time, the problem that we give you is more simplified. Then you only have few things. Some of the things is going to be equal to 0. If you don't have a spring, you don't need to consider about U sub S. If you are moving along a flat, like horizontal surface, you don't need to worry about the gravitational potential energy, because it's all happened on the same level. So that's the general form. Everything here is in energy, so the unit should be in joule. and joule is equal to Newton times meter. So this is joule, which is Newton times meter. One of the things that we didn't put a lot of time talk about, which is the power. Power is by define is the work over time. That means how much time does it take for you to deliver a certain amount of work? We look at the efficiency of delivering work. That is power. Power has a unit which is called watts. Watts is defined by joule over second. That is the watts. Chapter 7, we talk about this Wednesday. We put this one to be the last topic. This one actually is very simple. Only 3 things I want you to remember. One is the Newton's law of the universal gravitation. That is the F of G. So F of G is the attraction force between 2 elements with the mass, which is equal to G as a constant, the mass of 1 times mass of 2 divided by the distance squared. The distance is the distance between 2 objects. Okay, so if you have a 1 object here and the other object here, this one has the mass of 1, this has a mass of 2. This is going to be the distance. When we look at the distance, is from the center of the mass of 1 to the center of the mass of 2. So this is our D here. G is a constant. We will give you the constant in the exam, so the formula sheet should include this one already. The other thing about the gravitation is that we know the potential energy is coming from the gravity. So you have a general form for the gravitational potential energy as well. Why do we call this universal? Because it's not only happen on Earth, it can also happen on different planets. Even for Sun, you are going to have the gravitational force and also the gravitational potential energy. If you can actually go there and try it, that's going to be the same. The one of kind of thing that we define for the gravitational potential energy is this. Probably is not obvious, because when you learn gravity, we always make the ground to be the 0 location. But when we define the universal gravitational potential energy, we define the distance at infinity to be 0. So if you have something far away from each other, then we say there's no potential energy, so the potential energy is 0. But if you bring things get closer and closer, you will start to have some like a change of potential energy. That change is that you're going to change more and more to the negative. So the equation that you look at from the book or from the formula sheet will have a negative sign for that. So that is kind of not that obvious, but you have to use the negative sign. Otherwise, when you do the calculation, you might get the wrong answer. Escape speed is the speed if you shoot something from any of the planets, such as Earth, and you want these things be able to escape from the attraction of the gravity. So you can actually get out of the space. That is the escape speed. Now that also have an equation that's in your formula sheet as well. Just make sure that you watch that. So it depends on what planet that you are. Therefore, it depends on the mass of the planet as well. So you can watch that, look at that formula. We're going to skip chapter 7.4, the Kepler law. There's something about the planet motion. We're not going to cover that in your exam. The next one is chapter 8. Chapter 8 talk about the momentum, impulse, collision, and the center of the mass. momentum that we use this symbol P. This is a linear momentum, and the momentum is a vector, so you should have an arrow on top of that. Impulse is also a vector, so there should be an arrow on top, just to tell you that it's not just a value, it also has a direction. The way we define a momentum is very simple. The momentum is simply equal to m times v, where v is the velocity is a vector. If you wanted to see how we define the impulse is equal to force times t, and t is the change of time, which is the time of the contact. So F is a vector, that's why the impulse is also a vector. And we do a lot of example about the conservation law, and the conservation of the momentum is one of the important one. And the condition for conservation of momentum is no external force. If there's no external force, then you have a conservation of momentum. So I want to emphasize the external. External meaning if you look at the momentum of a system, that external force is the force outside of the system. And for example, if you have like 3 balls, they are connect with each other, and you throw this one out, and suddenly there's like an explosion happen in the 3 balls, they will start to separate. And that explosion, the explosion is an internal war. It is an internal force. It's not external force because it happened internally. It doesn't create the explosion because something is hit on these objects. So this is so-called the internal load, and that internal force which would not change the conservation of momentum. So doesn't matter what kind of an explosion that is not counted as the external force. So momentum will always be conserved. Then we define the elastic and inelastic collision. So what is the difference between the elastic and inelastic? If you have 2 objects and they hit with each other, they separate with each other, but they are still moving. That is what we call the elastic. If they move together if the one object hits to another object, they move together and they stick together. That is what we call the inelastic collision. Now, actually, to be more precise, the inelastic should be defined as the perfect inelastic collision. There are chances that after you have the collision, they still separate, but during the collision, they will change their shape to accommodate the other object. That is so-called inelastic collision, but that is not like perfect. If that is perfect, that means one of the object is going to embed it into another object, and they start to move together. This kind of embedment is it just tell you that they will move together forever. If they are not perfectly inelastic, that means they will deform. They're going to change shape a little bit, and then they will recover to its original shape. In that case, there are certain moment they move together, but after they recover to the same shape, to their original shape, they will separate. So that is what we call inelastic collision, not the perfect inelastic collision. But in most of the cases, what we are interested is that doesn't matter which kind of collision that you always have the conservation of momentum. That's the important thing that you should remember. The last topic for this chapter is to determine the location of the center of the mass. So how do you determine the center of the mass? Well, there is an equation to tell you. If you have several objects, then you just use the coordinate of each one of the object and also the mass of each one of the object. So the equation will be similar like this. If you look at the book, this is the center of the mass at the x location that is equal to the total mass, which is a summation n sub I. This represents total mass. And on the top, you're going to have the multiplication of n times r. This one r, which is the r at the x direction of I. So each one of them has their coordinate. You have to write down their coordinate. And you just pick the same direction. In this case, this equation is for the x direction. You look at what is the x location of each one of the object. Then you can use this formula to find out the center of the mass at the x direction. The y direction is similar. Then over here, you just replace the x to as xcn to be ycn. Okay, the last chapter about the rotation. There are actually a lot of things in the rotation motion. We didn't go through the detail because most of the things that you already learned in the chapter 3, 4, and 5. There's so many of the similarity between the linear motion and the rotational motion. And if you look through the homework and look at the table that we give you in the formula sheet, you will find out they are related in certain way. But first, I wanted to emphasize on these two things. When you have a rotation, we can measure the rotation in a way which is how much distance it travel. The other one is that you can also look at the angle of the object is moving. So tangential will be more like the quantity along a line. Then the angular will be the quantity along a loop. So that is the main difference of these two. Now, an important equation for this one is this. If you have an object is doing a rotation, then it will have a rotational velocity, which is what we call the angular velocity. Angular velocity, sometimes we use RPM to represent it, and sometimes we will make a radian per second. So you have to look at what the problem give you. Sometimes you might need to do some unit conversion. So make sure that you know what that is. The R here represent the location. The location away from the axis, the rotational axis. Okay, so that is how you can convert the tangential. So this is the tangential, this is the omega. We also have a tangential and angular acceleration, which means if you wanted to find the A and you also know the radius of this disk or this circular things, you have to times another word called alpha. So alpha is called the angular acceleration, tangential acceleration is A. So these are the four things that you should start with. And then the book talk about the constant angular velocity, constant angular acceleration motion. They are similar to chapter 4 and 5. The thing you need to be careful about this is that when you are using the constant rotational motion, the n in the rotational motion will become this one here, which is the moment of inertia. Okay, so if you have a velocity in the linear motion in a rotation, it will become omega, which is angular velocity. If you have acceleration in a rotational field, this one will be our alpha. Okay, these are the symbol that we use to represent their quantity. And we also look at the torque. So we tell you how do you define torque. The torque is going to be force times the perpendicular one, right? So the torque is actually the force times the perpendicular distance. That actually is what we call the lever arm. So you gotta be careful. The force has to be the force that is perpendicular to the lever arm. Okay, force should be perpendicular to the lever arm. Then you can find out the torque. Moment of inertia, we explain this a lot also in the lab. I don't want to say any words about this. There is an equation which is mr square. The n is the mass, r is the distance between the observer to the thing that is doing the rotation. The next one is about the moment of inertia. Again, oh, sorry, I already said this one. This is something, if we test you this one, we will give you those formula because different shape has a different way to calculate the moment of inertia. We're not going to give you a very complicated shape. So it's going to be similar like the rectangular, circular, that kind of things, a simple graph. Now, rotational also has a kinetic energy and a potential energy as well. So kinetic energy, in terms of kinetic energy for the rotation, the K of the rotation is equal to 1/2 I omega squared. Okay, so if that is the tangential, that is 1/2 mv squared. So you can see they actually analogy to each other. Omega is similar to the v. Moment of inertia is some like a simply equivalent to the mass. So the mass in I is very similar. The I has a unit, so for the I, the unit is going to be kg times meter square. I was grading your lab, and a lot of people use kg divided by a meter square, which is wrong. So make sure that in the exam, if we give you this problem, you don't write it as the wrong unit. We didn't spend much of time talk about the angular momentum. We just give you a concept about that. Let me define the angular momentum, which is the L that you can see from the textbook, the L. So the L is equal to I omega. And if you think about the other momentum, the P, which is our linear momentum, equation for that is m times v. Okay, so omega and v, they both are vector. Di is equivalent to the mass. So that's why we write equation side by side. Just want to that you know that they are actually very similar. We also have a conservation law for the angular momentum stuff, like the example we told you during the lab, ice skater. They stretch out the arms or hold an arms back will have two different kind of a posture. And one of them is going to have a higher rotational energy, and the other one will have a lower, right? So it depends on your moment of inertia and also how fast this rotation is. We will show you some example after this. And there's the last topic I wanted to emphasize here is that one of the exam problem is going to be static equilibrium. And I hope that you know how to solve these kind of problem. We actually go through this in the class, so everybody should get 100% correct on this problem that we give you. All right, so I'm done with the topics that I think I want to emphasize. I'm going to work very quick. I won't solve it, just give you an idea how to solve it, and you can try it by yourself, which are some of the example here. First example is about the work and energy. And they tell you the mass of is accelerate from rest to frictionless surface. All these words in a statement are important to your solution. So this is the mass of the object. It starts from rest and is frictionless. And final velocity is this much. But they give us a graph. What this graph is what is the force. This is also important for the honor section. Force is not a constant. It depends on position. It depends on the position. So how do we solve this problem? They say, what do they try to solve is this one here. They try to solve the F max. They try to ask you, can you write the F max in terms of N, which is the mass, V is the velocity, and the numerical factors. Okay, so how do we approach this problem? If you have a force and you actually move along a distance, right? X is represent the position. So you start from the 0 and then you give a force. This force is a constant force at the first 30 meter. So up to here, force is a constant. The force is equal to force max. Okay. But I didn't tell you F max, you have to find Fx. So how do we solve this? Well, if you want to find this, you have to use the idea called the work in kinetic energy. It's the very beginning of this book. They say, if you do work, you are changing the kinetic energy. So that work will change kinetic energy. The change of kinetic energy, meaning the kinetic energy at the final minus kinetic energy at the begin. But if we want to find the kinetic energy, then we have to use that equation. The equation is 1/2 and VF squared minus 1/2 and VI squared. Do we know the V sub F, V sub I? Well, you look at the problem, they say start from the rest. So initial is 0. Final velocity is 12.5. This is 12.5 meter per second. How much mass this object is 22 kilogram. These are the given information. That is equal to work, right? That is equal to work. So on the right-hand side, you can see I only have 1/2 mVf squared. And all these are like a numerical number. So you can actually just use that to get the total work. But we are not interested about the work. We actually interested about this F max in this graph. This carry an important concept about how we actually get work from graph. If you have a graph, the work is equal to the area under the curve or between the graph and also the what am I trying to say? And the axis, yeah. So and the x-axis. So you can see the area is not the same, and also if you go down to the bottom, this will be a negative work. If they are on the positive, this is positive work. Okay, so the work is simply just the area. Then let's see how we can find the area. So work is the area and how do you find the area for the first shape before we go to the zero? That one is actually a trapezoidal. I'm not sure that you know how to find the area of the trapezoidal. If needed, then you can write down this equation in your formula sheet. So to get the trapezoidal area, you need to know what is the long side of this trapezoidal. So here is the long side. You also have a short side, which is the top one, that is the L of 2. And you need to find the area. You have to modify the height of actually the distance between the L1 and L2, which is this one here. Okay. So that one is related to what? That one is related to F max. So we can find this one here. So let me just write down. This is the this one here. This is an area 1. This one here is the area 2. I add these two together, I will find out the total work. Okay, this thing that people will make mistake is that you are going to get the first one, which is this much of area. And the second one here, you cannot simply just add them, because the second one is a negative work. So you have to minus this shape here. That is the total work done by this 100 meter. Okay. Again, you cannot simply add them. You have to actually do a subtraction to get that. So how do we get the first one? The formula is this. You have 1/2 times the long base and the short base, then you have L1 plus L2, and then you multiply with the height of this one. So the height of that one is actually the F max. Okay, now do we know L1 and L2? That is, L1 is equal to 50. The L2 is equal to 30. Okay, so that is how you figure out the total amount of the area above the zero crossing point, which is at the 50 meter location. Then you use the second the same way to find the second one. The second one is also a trapezoidal. This one is a trapezoidal. You can say this is the L1, this is the L2. In that case, your L1 is going to be this much. This much is 1/3 of F maxima. Because this is a 1, 2, 3, which is a positive. Now you go down, this will be negative. So when you calculate this, you have to subtract the area too. Okay. So this one will be the L1. Wow, I have another L1. Let me put 3 and 4. Then L3 plus L4 times the height. So what is the height for this? The height is right here, is the F maximum divided by 3. And that is how you're going to calculate this. I'm sorry, this should be negative. I forgot. This should be a negative here. So that's your total work. Once you find the total work, then how do you solve this problem? Well, if you find the total work, and then you can make the work into kinetic energy. So the work equal to the change in kinetic energy is this equation here. I have the KEI equal to 0, so this cancel out. And all I need to do is to find how much work and also what is the kinetic energy at the final. And that is how you solve this problem. Okay. All right, the second one is very similar to the previous one, but it's only about the energy. If there's a friction force, then you have to have the friction force as the force will do work. But in this one here, no, you don't consider of that. The only thing that you have is that you are going to have a kinetic energy that will transform into a potential energy. And this potential energy is not use of G, this potential energy is use of S. Okay, so let's look at the problem here. They told you 0.85 block, so this is a 0.85 kilogram. Kilogram is the unit of the mass. Traveling with a speed which is 2.1 meter per second. So these are the information that's given. Now, the last information they give you is that the spring will stop over a distance of 0.15. Okay. Another thing we see from here is this speed. So that speed is 2.1 meter per second. Moving to the right. Now, they told you this it will stop over a distance of 0.15 meter, which means afterwards, you're going to have the system like this. So the block is not in front of, like far away from the 0.85 kilogram. It has the, it will compress this. So if you look at the distance from here to here, the difference of this is given a 3.3 meters. Well, is it? No. Oh, they give you this 0.15. Okay, so the 0.15 represent the spring constant kx. The x is represented by this 0.15 meter. So I told you the best way to solve this kind of problem is to create a table. So always I encourage you to create a table to solve this problem. Here I'm going to show you the table I will use. So the first column is the stage. I'll make the stage 1 and stage 2. Then we look at what are the kinetic energy, potential energy, and possible has some work as well. So here I have a kinetic energy, here I have a potential energy, but the potential energy in this case is related to spring. We don't consider gravitational potential energy because they are working on the flat surface. There's nothing going to change that. So how do you define stage one? Stage one is actually this stage. The stage one meaning the block is moving toward to the spring and it's getting closer and closer until it stops. So from the beginning of the moving to the stop after it hits to the spring. The second stage is that once you hit it and you after you move to 0.15 meter, what happened to the object? The object will stop again. Okay, so that is the two stage that you can define in this way. After you define the stage, then you use the formula to find out these values. So kinetic energy 1/2 mv squared. Potential energy for the spring is 1/2 kx squared. And you look at stage one, do we have kinetic energy? The answer is yes, because you are given with the mass, you're given with the velocity 2.1. So you can find kinetic energy. What about the potential energy? Well, the potential energy of the gravity is equal to 0, but for the spring, your kinetic energy is 1/2 kx squared. The k is the spring constant. Okay, and you look back to the problem, they told you, well, 0.85 block traveling with the speed 2.1 stopped over a distance of 0.15. So the x-axis, the longest distance is 0.15 meter. And then, so what is the stage two situation looks like? When this block moves all the way down to the right, eventually it's going to stop. So when it stops, you don't have a kinetic energy. But do you have a potential energy due to the spring? The answer is yes, because we just kind of show you this is the equation to get the force. So 1/2 of kx squared is going to be the kinetic energy, the potential energy at the end. So if you look at the table, it's very straightforward that this is the case that you transform kinetic energy into potential energy of the spring. And you just simply that an equal that you can solve this problem. So this problem has two stages. First, then use the given data to find one thing that we don't know, which is this one here. This K here represents the spring constant. So you use these to find the spring constant first. After that, they want to ask you what distance will 1.3 kilogram block travel after making contact with the spring. So that is how you can solve this problem. Okay. I didn't calculate this, but it's very straightforward. So if you, let me just write down the first one. If you try to solve for the K, this is what you are going to do. You have a kinetic energy at the stage one, which is 1/2 m, and is 0.85. And V squared, V is 2.1 meter per second square. So that is the kinetic energy at the beginning. potential energy at the beginning is equal to 0, then that will be equal to final one. The final kinetic energy is 1/2 times the K and the X squared, where the X is, let's see, what distance would I, oh, they told you this is a 0.15, so 0.15 squared. That's for the first stage. Now the second stage only have this one here, so that should be equal to 1/2. Oh, I already wrote it. So, okay, so these two has to be equal, and then you can find the K. So 1/2 can cancel out, then you should be able to find K. Again, this K is the spring constant, okay? All right, let's look at the next one. The next one is about the gravitation force and energy. So to find the solution for this one is that the problem is given in this way. We might give you the Earth and Moon, we might give you different things. So you have two objects. Let's say like two circular objects, one like this and the other one like this. And they tell you they're going to put third things. The third object is going to be somewhere like this. And let's make this one to be the Earth. Let's make this one to be the Sun. So Sun is going to pull the object. The Earth will also pull the object. So this one is going to be the force to the right. And you also have another force pull to the left. And this force is the Earth on the Sun. Oh, no, not on the Sun, on the object. Okay, so one force goes to the right, one force goes to the left. And at a certain point, they can cancel out. It depends on the distance. Okay, so it depends on the distance. You have to find the distance. And how do you find the distance? Well, you might need to make an assumption. If you don't know the distance, you just say, oh, this is the X. And this will be some distance minus X. Okay, and you were given with this one here, which is the mass, is not the distance. So how do you find that distance? Well, we didn't give you that information, but you can look on the textbook. They will have a distance between the Earth and the Moon. Then you will use the number to minus X to be the difference. Okay, the equation that you need to use is this, is the G M1 M2. Now, if you solve this problem, G is the sand. Let me just write the whole thing here. You try to find where you have the net force equal to 0. And that net force is coming from two. One is the sun on this object, actually is moon. Sun on the moon, plus the force of the Earth on moon. Okay, and which one is positive, which one is negative is not that important, as long as you know one should be positive, the other one should be negative, because they go to the opposite direction. And so if you look at the first one, if you want to calculate the first one, that's equal to G times the mass of the sun times the mass of the moon, divide by these distance. Let's say this is an X, this will be the X squared. And you have another one which will be negative, because we said the force has the different direction. This will be G again. This will be the mass of the Earth instead of the sun multiplied with the the mass of the moon. Then you're going to divide by sun distance minus x, where d is the distance from the sun to the earth, or earth to the sun. So here will be d minus x squared. And you make this one equal to 0, you solve for d. You solve for d. That's how you can get this things done. Okay, the last thing I want to talk about is about the linear momentum and the impulse. The first question here is that you have a 10 kilogram block on ice. By using the ice, we're going to assume there's no friction. And it moving to the east, and they give you 8 meters per second. So just simply draw that. This is this 10 kilogram moving to the east, and the speed is 8 meters per second. Okay, that's the first one. Now let's say it will collide elastically with another block. This block is 6 kilogram. It's also on the ice. There's no friction on that one. So the second object is here. This one is 6 kilogram. And let's say the 6 kilogram actually was moving at 4 meters per second. So this one also moving with a 4 meters per second. As you can see, the first one has a higher speed than the second one, so it's going to catch up to the first one if it's at the front of that. So eventually they're going to collide. So they tell you this is elastic collision. So elastic collision meaning when after they hit, they will separate. They're separate. They could move backwards, or they can still moving in the same direction, and just one move faster, one move slower. So how do we solve this? They want to find the velocities, so that if this is a 1, whoops. If this is an object 1, this is an object 2, then they want to find the V1 plus V2 and the V2. The plot meanings afterwards, okay, or the final velocity of that object. What is the thing that you use to find this solution? What is the conservation law that you can use to find this solution? Whenever you have a collision, momentum always conserved. So you use conservation of momentum. Conservation of momentum meaning the momentum at the beginning equal to the momentum at the final, or the change of momentum, which is equal to momentum of final minus momentum of the initial. It should be equal to 0 because they equal to each other. Okay, so that's how you use the conservation law. So let's look at the conservation law. I have an initial is 10 times 8 plus 6 times 4, direction to the right. That's initial. So that my final should be also equal to this number. But what is the final equal to? The final equal to, again, same thing, the mass is 10 times V1 prime, which I don't know. I try to solve this. And also, you're going to have the second one, which is 6 kilogram times V2 prime. Okay, now if you look at here, I have 10 times 8 plus 6 times 4, that's 80 plus 24, that's 104. That's equal to 104 in total. But on the right-hand side, the PF, they have 10 V1, 6 V2. So you have two unknown. You cannot simply solve this problem by using this equation. You need additional equation. That additional equation in this case is kinetic energy is also conserved. And this is for the elastic condition. This will not work for the inelastic collision. In elastic collision, you don't have a conservation of kinetic energy. So kinetic energy conserved, meaning the beginning of the kinetic energy equal to final kinetic energy. So KEI equal to KEF. So what is the KEI? KEI is 1/2 10, M is 10, V is the V1 squared, and plus 1/2 of second mass, that is 6, and the V2 squared. That is the starting kinetic energy. The final kinetic energy is very similar to that one, except you're going to have the 1/2 10 times V1 prime, which is the final velocity of the first ball. The second one is very similar, 1/2 6 V2 plus. Okay, once you put a number in here, then you see, well, you have a second equation that you have to solve the two equations together in order to find the answer. Okay. Problem 50 is about the impulse and the force. So if you have an average force, meaning the force you treat it like a constant, you work on an object which is 0.2 kilogram ball moving at 20 meter per second, how much force that you have to apply to the object in order to stop it? So to solve this problem, that you use the change of a momentum equal to the impulse, where impulse is equal to the force times the time of the contact. This one is the time of the contact. Then how do you find the average force? So this is the average force. To find the average force, you have to find what is the change of the momentum. Okay, so what is the change of momentum? At the beginning, the ball is moving at 20 meters per second. But when you touch it, then there's no like a velocity, and then you have the force and also the time of the contact. Then the final momentum will be equal to 0. Initial momentum will be just the mass times the velocity. So if you put that into this equation, this should be equal to the m times v, where m is 0.200 and your v is 20 meter per second. So that is how you get the change of momentum. This is equal to the force average times the change of time, which is 0.025. And that's how you find the F average. Okay, sorry, I'm get over time a little bit. Let me finish these two problems real quick. The first one about the rotation is they give you angular speed of the rotating wheel. They give you the moment of inertia. So moment of inertia is equal to 0.33 kg meter squared. They tell you the kinetic energy of the rotation that is equal to 2.7 joule. Then how do you solve this problem? Well, kinetic energy for rotational motion, if you look at the formula sheet, the table, they give you which is 1/2 I omega squared. So you just simply use this equation. You can find the omega because I is given 0.33. Just remember this omega is going to have the unit called the radian per second. That is the unit for this one. So whatever you find out value is going to be the omega in terms of the radian per second. If we wanted to find the answer, which is not radian per second, then we want revolution per minute. This is the RPM. It's the same as the round per minute. Then you have to do a conversion, right? So 1 revolution is equal to 2 pi radius. 1 minute is equal to 60 seconds. And you use this, you can do the conversion. The last one here is the CD player. It has a speed and it will change circular track on the CD. CD player is rotating at the 300 RPM. And they read another track of the angular speed, they increase to 450 RPM in the time of 0.75 second. They want to calculate the average angular acceleration in terms of the radian per second squared. So how do we find the solution for this case? Okay, so you change from 300 RPM to 450 RPM. That means you have an acceleration. And how much time does it take? It takes 0.75 seconds. It is similar like you are traveling with like a 30, like let's say 300 meter per second. Then you, in 0.75 seconds, then you change the speed to 450 meter per second. That's what this means. But this here we have is a rotation. You can assume this one is going to be a constant acceleration motion. If this isn't the case, then you have an equation very similar to the linear motion. So you have a final angular velocity, which is this one, equal to initial angular velocity, which is this one, plus the acceleration times the time. What is time? Time is 0.75 seconds. And you need to find alpha. But before you do that, you have to find these two in terms of the radian per second. Okay, you have to change this one to radian per second. Also for this one. And then you can find a solution. So this is how you find a solution for this case. Okay, so this is the end of our lecture for the review. I'm sorry I get over a little bit. Here I want to show one example for the honor section here. The example I give you here is the work definition. So work definition for a non-constant force